Recursively defined sequences arise anytime you have a situation where you can compute the next term of a sequence from the preceding term in a natural fashion. This is something that happens quite a bit when you are working with something like compound interest, and that's is going to be our introduction, in fact. And after that introduction, we're going to talk about the formal definition of recursively defined sequences and a few more mathematical applications. All right, so let's take a look at compound interest. If you invest P0 at an annual interest rate of R, then the initial amount of money is P0, and the change from one year to the next year is that you get a rate of R added to your principal. So that means that the principal after K years is going to be 1 times the principal that you had after K minus 1 years. The investment stays in the account, plus your R, your interest rate, we're going to consider as a decimal, so R times your principal from the previous year has been added. And yeah, let's take a look at that in a spreadsheet for a $5,000 college savings account at 8% interest, which would be a wonderful interest rate indeed. All right, this spreadsheet doesn't start at 0, so let's go ahead and start at 10. That way we know that whatever our row number minus 10 is, that's the number of years that has passed. So you start with $5,000 in the account, and then what you have is you have that you take 1 plus 8% is 0.08, and you multiply that with what you had in the previous year. And so yes, 8% of 5,000 is 400. So after 1 year you will have $5,400. Now suppose that this was an investment that is made at the birth of a child, and at 18 it is hopefully then time to qualify for and go to college. So we would want to know how much is in the account after 18 years. That would be what happens in row 28. And according to this computation, the $5,000 investment has increased to $19,000. Now, if you are looking at 8%, 8% times 20 years is 160%, which means that without compounding, you would have expected that this would have close to tripled, but it actually, because of compound interest, it has close to quadrupled. 160% actually isn't quite tripling. If you add 160%, that's just multiplying by 2.5. So because you now also earn interest on the interest, the investment grows more rapidly, and that is of course what people like to see when they invest money. Now the flip side of investments is, what does a bank do that has money from a customer and pays interest on that money? That bank loans money to other people who need that loan for a car or for a house. And so if you have a loan of B0 at an annual interest rate of R again, and you want to pay off $8 per month, well then the initial amount of money that you have to pay off is B0, and the change from 1 month to the next month is given by that next month's balance in the account is the previous month's balance, which has not changed, except that the prorated interest rate, the prorated interest has been added on, and your payment has been subtracted. So let's take a look at that in a spreadsheet for a $300,000 mortgage at 7% with monthly payments of $3,000. This is somebody who certainly has larger financial means than I have, would pay or would be able to pay. And the principal, however, the principal, not the principal, the principal is the same thing as what we had before. You look at this and you have a $300,000 initial balance, and what happens now is that after a month the original balance is still there, and the interest has been added on, 0.07 in this case, divided by 12, because the interest rate is prorated over the year, and then you subtract $3,000 off of that, and you realize that yes, you have paid off a bit, but that is because the $3,000 payment actually is an accelerated mortgage. That is a mortgage that I think runs pretty fast, because if we're looking at this after 2 years, that would be row 34, you've paid off, well, you've paid off close to $30,000, or a little bit more than $30,000 actually, but notice that you have given the bank $60,000. In fact, over $60,000, because 24 months times 3,000, that's $72,000. That is how banks make money, and the one thing that I should have adjusted in my examples is that certainly a bank will lend money to people at a higher rate than it pays interest to its investors. This computation, however, is very useful, because if you now want to know how long it takes to pay off this mortgage, well, you would just keep running this spreadsheet until you hit 0. So let's see what happens after 10 years, which is 120 months, which would be row 130 here, because we started in row 10. After 10 years, you still owe $83,000, but now the payoff goes pretty quickly. 15 years is 180 months, and 180 months would be row 190 here. And after 15 years, actually, it is paid off. In fact, the whole mortgage is paid off after about 150 months, which is something that personal philosophy I would certainly recommend to anybody who has debt. First of all, the best thing, of course, is to not incur debt at all, but if you have debt, pay it off as fast as possible, so that that interest no longer goes to the bank, but actually goes to yourself. And technically, because you could just keep up these payments and put them into your own savings account. All right, aside from this kind of personal philosophy, the mathematical definition that underlies the whole thing is that a sequence is defined recursively if and only if we are given an equation to compute the next term from earlier terms, and that equation is usually of the form ak equals some function of ak minus 1, ak minus 2, all the way through ak minus j. It could be that the recursion reaches back farther than just the previous term. It could reach back to the previous 2 terms, previous 3 terms, and so on. Or ak plus 1 being, depending on f of ak, all the way down to ak minus j plus 1. You've also already seen that, because I think in the compound interest I had a formula for pk, and for the loan payoff I had a formula for bk plus 1. That's basically the same thing, only expressed differently. That equation is also called the recurrence relation, and you need to have enough initial values to start the process. So you need as plus 1, all the way to as plus j minus 1, so that as plus j can be computed from these values. And for our compound interest relation, then, for example, the recurrence relation was f of pk minus 1 is 1 plus r times pk minus 1. And r was a constant there, right? It was our interest rate. And for bk plus 1 equals bk times 1 plus r over 12 minus a, the recurrence relation was f of bk being bk times 1 plus r over 12 minus a. So the recurrence relation can be that ak is expressed in terms of previous terms, or it could be that ak plus 1 or even ak plus 5 or something like that is expressed in terms of previous terms. And again, here r and a are constants for the loan example. As a visualization, the recurrence relation essentially is a black box that you feed your value, your initial value a0 in. What this black box then does is it gives you a1 being f of a0, and the recursion idea is that you now feed that value, which is now a1, back into the black box, and the recurrence relation gives you a2, which is f of a1, that is being fed back as a2 into the recurrence relation, and gives you a3 being f of a2, and so on and so on. If we do that now in a counting example, we can talk about factorials. And so we could, for example, ask ourselves, what's the number of ways to seat 6 people at a table with 6 chairs? Well, the first person has 6 chairs to choose from. That person sits down. Now we only have 5 chairs left over, so the next person has 5 chairs to choose from. That person sits down, the next person has 4 chairs to choose from, and then the next person has 3, 2, and the last person has only 1 chair open, has 1 choice. The definition of this function is that the factorial function k factorial is defined for positive integers k by k factorial being k times k minus 1 factorial. So it is always k times whatever we had from the previous one. And 1 factorial is defined to be equal to 1. Formally, we also define 0 factorial to be 1, and that is because sometimes in certain expressions, such as, for example, the terms of Taylor polynomials, which we will also talk about, those terms contain the factorial function and may need to be evaluated at 0 also. And when you do that, then these formulas are just most consistent if we choose 0 factorial to be defined to be 1. Okay. Other than that, of course, this recursive definition can be resolved into 6 plus 5 plus 4 plus 3, 6 times 5 times 4 times 3 times 2 times 1. But that is something where this recursion can be programmed into a computer. This not so much, because you can't tell a machine, hey, just take your number k and multiply it with all the smaller numbers until you're done. That would be something that has to be programmed as a recursion or as something where the recursion is being resolved. As an example, if we now want to find a closed expression for a product 1 times 3 times 5 times and so on times 2n minus 1. Now that example looks like it comes out of thin air, but there are processes such as the solution of certain differential equations where computations may really come up with a situation where you need to have the product of the first 2n minus 1 odd integers, and when you want that, then you want to have a closed expression that you can type into a computer, because magic 3 dots, that's something that a computer doesn't work with. So what would we do? Well, 1 times 3 times 5 times and so on times 2n minus 1, if I would just stick the even numbers in there, I would get a factorial. And so the even numbers that are missing are 2 times 4 times 6 times and so on times 2n. And certainly I can't just multiply by those, because that changes the expression. So we do exactly what we also did in the previous presentation where we were after a limit, and that is we multiply by 1. We expand with the expression that we want. And now we just sort things a little differently, because now the numerator is 1 times 2 times 3 times 4 times 5 times 6 and so on all the way to 2n. And the denominator is 2 times 1 times 2 times 2 times 2 times 3 all the way to 2 times n. Well, we see that the numerator is 2n factorial, and we see that in the denominator we have n2. So that means we have 2n factorial in the numerator. We've got 2 to the n that we can factor out in the denominator. And then we are left with 1 times 2 times 3 times all the way to n, which is n factorial. And so the closed expression for this product is 2n quantity factorial divided by 2 to the n times n factorial. Now we're going to talk about limits of recursively defined functions, and that's already the last part of what we're doing here. And to compute limits of recursively defined functions, we first have to actually establish that the limit exists. And to do that, we need some more definitions. A sequence is called non-decreasing if and only if for all k we have that ak is less than or equal than ak plus 1. So it is not the definition of strictly increasing, because we also actually allow equality here. Also, we allow a little bit of stagnation, and so that means the sequence is going up or stagnating, but in particular it is not decreasing, and that's where this strange word that some people, including myself, don't necessarily like too much, even though it's accurate, it's that the sequence is non-decreasing, so it's going up or stagnating. AK is called non-increasing if and only if for all k we have that AK is greater or equal than AK plus 1, so that means that the next one is less than or equal than the previous one. Yeah, I got confused here by the reversed inequality. Again, that just means that the step from one term of the sequence to the next term is a step down or a stagnation, which means what the sequence doesn't do is increase. So that's where the accurate description of non increasing comes from, even though some people, including myself, would rather say this is decreasing and then indicate the strict inequality by saying strictly decreasing. Okay, that being either way, this is the more common notation, so that's what we stay with. And if a sequence is either non-increasing or non-decreasing, then we call it monotonic. And there is a very important theorem, and that is the monotonic sequence theorem, which says that if you've got a sequence that is bounded, which we defined in the previous presentation, and monotonic, then the sequence converges, or more precisely, if you have something that is bounded above and non-decreasing, then it converges, and if it's bounded below and non-increasing, then it converges. The proof, well, actually, the monotonic sequence theorem can be used as an axiom for the real number system, which means that we're not going to prove it here because we did not axiomatically define the real number system. In terms of a visualization, if we have a sequence of terms a1 going up to a2, going up to a3, going up to a4, going up to a5, going up to a6, and so on, and that sequence ultimately has a bound here somewhere, well, then it stands to reason that this growth ultimately has to peter out somewhere between the terms and the bound, and wherever it peters out, that's where the limit is. But that is where we actually need an axiom such as the monotonic sequence theorem, which then in fact distinguishes the real number system, because it says that the sequence can't aggregate somewhere where there is a hole in the number system, such as, for example, the place where root 2 ought to be is a hole in the rational numbers, right? So this is something that actually becomes fairly sophisticated and is something that you can learn more about in an introduction to proof classes where the real number theorem is discussed, is constructed maybe, or in an advanced calculus class where the real number system may be introduced axiomatically. Either way, we're going to use the monotonic sequence theorem to show that the sequence that is recursively defined by ak plus 1 being 1/2 ak plus 7 and a1 equals 3, we want to show that this sequence is bounded and non-decreasing, and after that we're going to find its limit. Well, so to show that the sequence is non-decreasing, we have to show that ak is less than or equal to ak plus 1. So first we note that a2, which is 1/2 times 3 plus 7, which is 5, is greater than 3, which is a1. And what we're now going to do is an inductive process where we're going to use that ak minus 1 is smaller than ak, and we're going to deduce from that that ak is smaller than ak plus 1. So from ak minus 1 smaller than ak, we can infer the following. Ak minus 1 smaller than ak means that ak minus 1 plus 7 is smaller than ak plus 7. That means that 1/2 ak minus 1 plus 7 is smaller than 1/2 ak plus 7, and that means that ak is smaller than ak plus 1. So what do we have here? We have that a1 is smaller than a2, and whenever the previous term is smaller than the current term, then the current term will be smaller than the next term, and that means that the sequence will keep on increasing, so that means the sequence is increasing here. This is something that certainly trains us quite a bit in working with inequalities, which is something that is a good skill to have for advanced classes where you either need to work with numerical estimates or where you're going to do proofs that involve inequalities, such as in an advanced calculus class. And we're going to also work with inequalities for boundedness. So a1 is equal to 3. Well, what's a good bound for this sequence here? We're always taking the average of the current value with 7. So 7 probably is a good upper bound here, and we know that a1 is smaller than 7. Now from ak smaller than 7, we're going to infer that ak plus 1 is smaller than 7. Because if we know that a1 is smaller than 7, if we know that whenever the current one is smaller than 7, then the next one is smaller than 7, well then a1 smaller than 7 implies a2 smaller 7 implies a3 smaller than 7, and so on. So ak smaller than 7 gives us that ak plus 7 is smaller than 14, gives us 1/2 ak plus 7 is smaller than 7 again, and that means that ak plus 1 is smaller than 7, and that means the sequence is bounded above by 7, and that's in fact what we want to have, because bounded above and non-decreasing tells us by the monotonic sequence theorem that the sequence has a limit, and that limit now is something that we can compute. And well, because the sequence has a limit L now, because we have proved that the limit exists, we can take the limit on both sides of the recurrence relation. So we can take our recurrence relation, ak plus 1 being 1/2 ak plus 7. We can take the limit on the left and on the right. We just do that, and we realize the limit of ak plus 1 is, of course, L, just as well as the limit of ak is L. So we get L being 1/2 L plus 7. That gives us 2L being L plus 7, and then L being equal to 7, and that is already the computation. Now it is rather tempting to say, hey, I can just do the computation anyway, and that will give you a number, and if everything else is well defined, then the number will be the limit. However, there also are sequences for which you can execute the process that is shown on this last panel, and the sequence indeed diverges, which means that there is definite reason for proving that a recursive sequence is increasing and bounded, or decreasing and bounded, or non-increasing and bounded, and or non-decreasing and bounded, in order to establish limits, and that is because the computation alone doesn't tell the whole story. With that, I'll leave you to probably some limit computations on the homework, and depending on how your curriculum is designed, you might now go into more work on sequences as they connect to continuity of functions, or in a more standard curriculum, the next thing you're going to talk about is series of numbers. Either way, I'll see you there.